And now we start with the discussion of hadron-hadron collisions. We've done a lot of preparatory work. We've discussed the plus and minus collisions and deep inelastic scattering. Now we also discuss hadron-hadron collisions and their interplay with the other types of collisions. Now, we have seen how from deep inelastic scattering, a large gluon parton distribution function arises, particular from the deep inelastic scattering experiments at moderate and high Q squared for proton, antiproton and proton-proton collisions. These parton distribution functions are a necessary input to arrive at any prediction that even remotely resembles what the physical reality observed in a collider. So we need to, as we've discussed at the end of previous lecture, we need to assume a factorization of the physical processes at a specific scale, which we call μf. μf is an arbitrarily chosen scale below which we say we have soft, non-perturbative, but process-independent parton distribution functions. This is what we put in the blue box here. This is what we've discussed in the last lecture, the parton model, the quark constituents, the gluon PDF, as they describe momentum fractions of the partons in the proton. So these are the blue boxes. And then above the factorization scale, we assume that there is a hard, that means highly energetic, parton process. In this case, two gluons collide and exchange a quark, which is perturbatively calculable in quantum chromodynamics. So the μf scale must be much larger than 1 GeV, and it must be in a regime where the strong coupling is low enough to allow a perturbative expansion. This is an assumption. This need not be realized in nature. It is realized in nature only up to certain accuracy, and in precision observables, in precision measurements at hadron colliders, there is a small sensitivity to violations of the factorization, in particular when remnants of an interacting proton interact with final state quarks, for example, that come from the hard process. Long story short, this is a theorem that's only true to good accuracy, but isn't a first principle feature of the standard model. However, it allows us to write down a general formula relating the hadron level with the parton level. The parton level is the level where the partons live, quarks and gluons, as we've really discussed extensively now. So we have a parton level cross-section, sigma hat AB. A and B labels the partons. So that runs over all the 5 quark flavors. Usually the top quark is neglected, but up, down, jump, strange, and bottom are included, as well as the gluon. Then the parton momenta are x1 p1 and x2 p2 for the two momenta entering the parton level cross section, and the distribution of these values x1 and x2, it is now given by the parton distributions. Here the parton distribution functions are written as FAP, which means which describes the probability to find a parton of flavor A, so one of the quarks of the gluon, inside a proton, that's the initial state particle, of a momentum fraction x1. And these two probabilities have to be multiplied because we have two initial state partons, at least for the processes that we consider here, and then integrated over the whole X range and summed over all the parton species. This is therefore only doable by, typically it's only doable by computer code for realistic cases. I show you an example. The complexity arises from the need to sum over all the parton pairs and the integration, of course. And in summary, even the simplest processes need sophisticated simulation tools. Just to give you an example, here is a die-jet process. So this is the production of, for example, two quarks ejected in opposite direction at the interaction vertex, and the quarks, as we've discussed before, hadronize into sprays of particles, which are jets. But if you want to compute this, you have to sum over all the parton reactions that produce two partons in the final state. And since we cannot tell apart in a hadron collider, we typically cannot tell apart a gluon from a quark, you have to sum over all these leading order diagrams here. There's plenty of them. So you have initial state quarks, you can have a gluon scattering a quark. These are all T-channel diagrams, but there are also S-channel diagrams that I omit. Well, here is a few S-channel diagrams, the last two. So two gluons produce a quark-antiquark pair, or two gluons scatter off and produce two gluons. So all of these produce matrix elements that can be calculated perturbatively. Here's the tree-level contribution. One usually must include at least the next to leading order, not corrections at the next to leading order in the 30% of this 30% size are not unheard of. Typical NLO corrections at Hadron Colliders can be, depends on the mass of the particles that are produced, but can range anywhere from a few percent to even a factor of 2. That's why these calculations are not something that we do by hand in the lecture. And even if that matrix element has been calculated, we need to multiply it with the parton distribution functions, which anyway are known only numerically, summed over and integrated over. Good. However, if that is done, exquisite agreement of theory and experiment can be achieved. The example I'm showing here is the highest transverse energy event from observed in the CDF experiment at the Hadron collider with a 2 TeV center of mass energy in the proton-proton rest system. We see here on one axis our pseudo rapidity, that's eta. Those were two central jets. They were in the center of the detector around eta equals 0, and this other direction is the azimuthal angle from 0 to 360 degrees. And the highest energy, the highest sum of transverse energy observed was 782 GeV, so almost half of the center of mass energy of the protons was converted into transverse momenta of two light partons, so either a quark and a gluon, we don't know, and those then hadronized into the final state, showered and hadronized in the final state particles, as is depicted here in this the transverse view. And well, that's a to observe such high, to correctly predict the occurrence of such high energy, highly energetic events is a huge success. And not only here, I mean, these are the highest square root of S. It works beautifully over all transverse jet momenta ranges. So what you see here is the D0, that's the other Hadron experiment. Run 2 at square root S of roughly 2 TeV. And you see the spectra extending over 6 orders of magnitude. The Y is the rapidity, similar to the pseudo rapidity. So three different corresponds to 3 different areas in the detector. And we see a very good agreement. So a collider project like the LHC is unimaginable without such predictions. It's impossible to design a search, for example, for the Higgs boson without knowing what the background is with digits, for example, as is shown here. Now, we can also relate the available energy in the parton-parton reaction to the available energy in the proton-proton reaction. The parton-parton square root S is just the sum of the initial state parton momenta squared. So it's x1 times p1, p1 is the proton momentum, plus x2 times p2. p2 is the proton momentum of the second proton or antiproton. If you square this, you find p1 squared and p2 squared, which give the proton mass squared, and you find a cross term. You can neglect the proton masses, and the cross term is 2 times p1 p2, but 2 times p1 p2 is just the square root s of the proton-proton system. So the center of mass energy in the parton-parton system equals x1 times x2 times the square root times the center of mass energy of the proton-proton system. So at the LHC, square root s is 13 TeV. So the square root s in the parton-parton system is 13 TeV times the square root of the product of these x values. So if you take a quark-quark annihilation, for example, you know we have a valence quark distribution where we often see values around 1/3. So the square root of 1/3 squared is 1/3. So therefore, in quark-quark annihilation, we often see parton-parton momenta of roughly parton-parton center of mass energies of roughly 1/3 of the initial of the proton center of mass energy. But because gluons have such a large PDF at low x values, in many cases, most of the reactions that we actually see are at lower momentum. They're gluon initiated. And in this sense, we say that we explore the TeV scale, the tera electron volt scale. That relation shown here is the reason why we don't really explore that. Although we have 13 TeV proton-proton center of mass energy, we really only explore 1 order of magnitude less. Factor 3 to factor 10 less is what we can achieve at the parton level. And at the parton level, this is where the reaction happens that we really want to investigate. Good, so it worked very well for the zero experiment and the Tevatron experiments. Now you can lean back and just look at the complex list of input data for PDF fits. This was before the LHC had started. This is a list that I copied from a paper from one of the collaborations, and what processes and sub-processes and which partons are affected when the parton distribution functions are determined. You see fixed target deep inelastic scattering. So here we have leptons firing at protons and neutrons. This was the experiment that we had discussed. You can do this with electrons and with muons. There are even in Minerva, for example, an experiment at Fermilab where neutrino beams are shot at nuclei. And you can, from the coupling of the neutrino via the Z and W bosons to the like quarks, the up and down quark in the nuclei, one can infer knowledge about the quark PDF from neutrino scattering. So that's a little bit you could say it's unexpected. It tells a lot about how far we've come. We now use neutrino beams to infer proton substructure information. And then, of course, we have the collider deep inelastic scattering. The top ones were fixed target. These are collider mostly from DESY. The plot I've shown with the Bjerken scaling, that's from DESY. It's these experiments. And then we can also include data from hadron machines themselves, proton-proton collisions, and so on. Now, the big picture, therefore, is the following. And I believe that's something that, if you're not told explicitly, it turns a while to figure out if you go, for example, to a high energy physics conference and you follow all the talks. It takes a while to get to the following picture. We have E plus E minus collisions that we studied at lab, so we understand the electroweak interactions even at the highest energy scales. We use this information to predict the interaction, the deep inelastic scattering interaction with the constituent quarks. Now, we don't know the quark and the gluon PDF, and we use sophisticated statistical methodology as well as the theory of quantum chromodynamics to fit the parton distribution functions. So one obtains parton distribution functions as are shown here in the middle plot. We've looked at these before. The X range extends even to lower values here. You see the gluon PDF is very large. It's scaled down by a factor 0.05. So we have a gluon PDF. We have up quark, valence quark, and down quark, valence quark PDFs. That's the outcome of the measurements of the proton substructure. And with this, we make LHC predictions. So in the LHC, we use the factorization theorem. At the LHC and at Hadron Colliders, we use the factorization theorem to take two of these parton distribution functions and combine them using the factorization theorem to make predictions involving hard scatter experiments. I put a famous example. The gluon interacts via a top loop to produce a Higgs boson. The Higgs boson can decay with a small branching fraction into 2 photons, and those 2 photons we can record. Now, it's impossible to discover the Higgs boson if you don't know your gluon content in the proton, because you don't know, if you would not know the gluon content in the proton at very high momentum transfer and at all values of X, you wouldn't know what size of a signal you would expect. So the whole story that we've discussed in the last so and so many hours is really just to give you an idea how much is needed to arrive at signal and background predictions that at the Hadron Collider that you can then compare with experiment. Now, once we have the LHC predictions, we can compare with measurements. And as we've seen on the previous slide, you can use collider data to feedback into the statistical statistical methodology that determines the parton distribution functions. So there is a loop here going on. And we continuously improve our knowledge of what's inside the proton by including more and more collider data, improving the predictions and then feeding the data back. That is the bird's eye view of contemporary high energy physics at the energy frontier. This is what we are doing. Most of the time, if you read a paper, you will find a search for, you will find a search or a measurement of a process that's of particular interest and that's just about reachable, like Z bosons, W bosons, top quark, Higgs bosons, but they all depend on our good understanding of the gluon and the quark content of the proton at all values of momentum transfer X as a function of Q squared. There is a danger here, of course. If something is not according to the standard model, Because we don't know the quark content, it's possible that we absorb it and we no longer see it. It's possible that nature is not described by quantum chromodynamics, but by a variant that looks very similar, but it's different. So these differences may be small, but if we, and they would show up when we compare predictions with measurements. There is a danger that we call these that we attribute the differences between data and simulation to the pattern distribution functions and absorb them. This is not possible in case of a resonance where something like the Higgs boson decays into two photons, because this gives a bump. It gives you, it gives a spike on, it gives a localized feature in an otherwise smooth background. However, it need not be so that the physics beyond the standard model is really is accessible by the energies that we can achieve at the energy frontier. So tera electron volt scale, it could be higher, and then we'd not observe bumps. We would observe mismatches in distributions between prediction and experiment. And those mismatches, if they are smooth, they can in principle be absorbed in the pattern distribution function. The hope is that eventually it will show up, because it's likely that a model beyond the standard model will affect all these processes that have a high degree of redundancy. It will affect those differently, and eventually the PDF feed will fail and will show such a difference. But I want to alert you to this danger. This is not. This is an actively developed field, and people are worried about absorbing deviations from the standard model in the pattern distribution functions. Although we're pretty sure it hasn't happened so far. Good. Let's talk about the jet formation in a little bit more detail, because next we're going to study how we can measure such signals in the subdetector components. Consider quark pair production, for example, in E plus E minus collisions, E plus E minus or hadron-hadron collisions. So E plus E minus goes into, in this case, maybe a photon or a Z boson, producing two quarks, a quark-antiquark pair. The process that's shown here at large momentum transfer is calculable in perturbative quantum chromodynamics. It is described by a matrix element. However, we know the strongly interacting particles with some probability can shower a highly energetic gluon, for example, and that gluon, it can split up into two more quarks. In doing so, the momentum reduces, and because the momentum reduces, the strong coupling increases, which makes that process even more likely. We had a simplified picture of this earlier. Here is a quark-antiquark pair. That's a classical picture. Quark-antiquarks move with a relative momentum, and color flux tubes are created with an energy density of roughly a Fermi with roughly a GeV per Fermi cubed. And once the energy threshold for the production of the pion is exceeded, a new quark-antiquark pair is created. And because this process continues to happen, the initially created quarks end up in a shower of particles. The two diagrams shown here are two different ways to simplify the same process that is only calculable in empirical models. Here's an example, it's a 4-jet event from the 205 GeV lab run. So it's E plus E minus, and two highly energetic, probably two highly energetic gluons were emitted, the particles that were clustered inside the jets have 4 different colors here: green, blue, black, and red. So that's a realistic picture of what a 4-jet event looks like in the detector. Good, we've discussed this. The picture that we are, the picture in theory landscape that we therefore have at the Hadron-hadron collider is the following. First, so that's a Hadron-hadron collider event, and we start here with the hard platonic interaction, which is calculable. Here we have the matrix element calculations, which follow the rules of the standard model. These are Feynman diagrams and Feynman rules, exactly equivalent to what we've discussed in the context of quantum electrodynamics. And then, as we had on the previous slide, after the decay of the heaviest particles, I'm not telling you which ones they are, but except this one, as a Higgs boson decaying to 2 p quarks. Once we have our highly energetic quarks, those emit, as discussed on the previous slide, gluons and quarks. So here you see the formation of a jet, and once the energy scale of the process involved in the shower reaches the hadronization scale, which is at the few GeV, then it makes actually no sense to speak of parton shower anymore. The reason is quite simply, and with this we've discussed, it's nothing new. You can, as we've said before, once a gluon, for example, is emitted from the initial state parton, the momentum is reduced and the process becomes more likely because the strong coupling increases when the momentum transfer is lower. This process goes on, and at the end, our description of our perturbative description of quantum chromodynamics breaks down because the coupling becomes roughly 1, which happens at 200 MeV. We stop the process usually at the few GeV or at the GeV, and at that point we translate ad hoc the gluon and quark fields into hadrons. This process is called hadronization. It's not something that nature does. Nature does all these things. Nature knows about strongly interacting fields. We don't know about strongly interacting fields, so we have to take our showered gluon and quark fields and translate them into hadrons. Protons, neutrons, lambdas, pions, everything, baryons, mesons, everything is contained there. And then we decay them. And once we've decayed them, we arrive at stable or metastable final state particles. And those then still emit electromagnetic radiation and decay further. So we are, when we consider detector physics, outside here in the final state, and we want to go back inside and infer what has happened at the hard scatter event. Not an easy exercise, but doesn't matter, makes life interesting. Once again, the cross-section at hadron colliders, because I think you can better understand it now. We have proton-proton collisions, so any of two partons inside the 2 protons in the collision react with a total cross-section of 80 millibarn. This is the dijet cross-section at the LHC. It's gigantic. If you ask for a heavy particle like a top quark pair to be produced, the cross-section is reduced by 10 orders of magnitude. The reason is simply that the parton distribution function has very low values for the energies that are needed to create such a highly energetic parton. I'm now going back here to our formula. You have 13 TeV accessible. You want to create the top quark pair, which has 300 GeV. So you need high numbers of average of x1 times x2 to achieve this total momentum. Unfortunately, most of the time you're picking gluons with a much lower energy, and hence you do not produce a top quark. And ultimately, that's the reason. Ultimately, that's the reason why the cross sections for the production of heavy final states, W boson, Z boson, top quark, 2 W bosons, and so on, is so low. On the other hand, all reactions happen at the same time. There is no energy scan necessary. The energy scan that we had to do at the plus E minus colliders to find the Z boson is not necessary, because x1 and x2 are random numbers that are drawn from the parton distribution function. So each event will have a new center of mass energy in the parton system. In other words, all accessible parton reactions happen simultaneously. The rate of top quark pairs is 1 per second. The rate of Z bosons is roughly 100 Hertz. And they happen at the same time. The top quark pair lives at 2 times 175 GeV, a Z boson at 90 GeV. But you get them at the same time because all accessible parton reactions happen simultaneously. That's the great thing about Hadron colliders. It's really a discovery machine. You do not need to scan, which can take years. Good. So we've discussed already the full Hadron-hadron event. I give you here the solution. The trained eye will find that this dashed line can only be the Higgs boson. In this case, it decayed to 2 p quarks. I gave that away. Here you have a top quark radiated a gluon. Then it decayed to a p quark and a W boson. The W boson decayed to 2 quarks. The 2 quarks showered, hadronized, decayed, and radiated. Here comes the detector and the rest of the lecture. But we did now discuss a substantial area of high energy physics. W boson can also decay to a muon. In that case, and that's what I want to stress, in that case, if the W boson decays to a muon, you're not subject to the uncertainties coming from the models of hadronization and decay, because the muon is a direct probe of electroweak physics. There's no strong interaction with the ensuing parton shower and so on involved. That's why at the LHC experiments, we practically record all the events with muons. Every muon above 35 GeV is recorded, and if there are 2 muons in the event, then we record them above, I believe, 27 and 8 GeV, if I'm not wrong. This is because events with muons are always the more direct probes of the TeV scale, because they're not subject to uncertainties from the parton shower and the hadronization. A few things that you really should know. These are the numbers that one should learn by heart if one reads any paper, any LHC experimental paper. The top quark always decays with a probability of 99.87 or so % to a W in a p quark. The W, once you get a W, it decays to lepton-neutrino pair with 11% per lepton species. So 11% for each electron, muon, and tau lepton. Together, that's 33%. The rest is decays to quark, anti-quark pairs. I forgot the anti-quark here. So the branching ratio of the W boson to a 2 quark pair is 67%. A Z boson has a branching ratio to dilepton pairs of 3.4% times 3, so 10% in total of the Z boson decay to leptons. This is great because at least in something like 10-ish or so percent of the Z boson decays, we can fully reconstruct it. We can't see the neutrinos from the W. We cannot perfectly identify the jet that belongs to the quark coming from a W. However, we can very nicely, because there is no, as I said now 5 times, I believe, because there's no hadronization for the leptons, if I have a Z boson with 2 of these guys, I can very accurately reconstruct the Z mass and compare it with the 91.2 GeV that it should have, and then I can be sure what I've seen. So roughly 10% or so decay to the Z bosons decay to leptons are 20%, twice as much decay to neutrinos, which is unfortunate. It just means that the Z boson completely disappears from the collider, from the hadron collider detectors. We cannot hope to have a neutrino interaction, and the rest decays to quark-antiquark pairs. The Higgs boson decays, I think, are also important. Higgs decaying to a pair of B quarks is the branching ratio is 58%. B quarks make B jets, so jets with a B meson inside them. These are hard to reconstruct. It's possible, but it is hard. Hence, at the Higgs mass of 125 GeV, which drives these branching ratios, 60%, they aren't lost, but it's hard to identify the 2 B jets inside the complex environment of other potential decaying heavy particles in this event. But there's 2.6% where the Higgs decays into 2 Z bosons, and the 2 Z bosons then decay to leptons. So we can observe the Higgs boson in the 4-lepton final state. And in fact, if you remember in the introduction, that's exactly the plot that I've shown you, a beautiful 4-lepton invariant mass peak at the Higgs mass. And with 4.2%, the Higgs boson decays to 2 photons. And the photons, if there's nothing else around, can also be reconstructed very accurately. Good. The backgrounds that you have at the Hadron machine, of course, depend on the signal that you're choosing. If your signal has plenty of electroweak probes like muons and electrons, then your background from quantum chromodynamics is very low, because it is very unlikely that a gluon or a quark produce a highly energetic muon or electron. The ratio of these processes, however, is very unfortunate. For each TT bar pair, we have 10 to the 10 QCD events. So it's not easy to get rid of 100 billion events per one interesting signal candidate. Good, but I should not whine around too much. There are other signatures predicted by the standard model that have very low background. These are mostly features that do not occur in quantum chromodynamics processes like jet production. So we think of the background as a complicated collection of processes like depicted here. So these are die-jet events. These jets, as we've said, produce final states with many hadrons, and a few features are very rarely predicted. One is high missing energy. Missing energy can be measured in the transverse plane by computing the transverse momentum sum, and events that are strongly produced and do not decay into neutrinos should be balanced in the transverse plane. If that's not the case, then one can infer that a neutrino has been produced, or maybe a dark matter particle. Both candidate processes would predict high missing energy. The quantum chromodynamics background would not, and hence missing energy is something to search. Missing energy is something to take into account when searching for physics beyond the standard model, production of dark matter, supersymmetry, and so on. Yeah. Then the Z boson decays to a lepton plus lepton minus pair. In other words, there is no boson that decays into a final state of leptons with the same charge. In fact, same charge dilepton pairs are extremely rare, and requiring that an event has a pair of leptons with opposite with the same charge almost completely removes all the standard model background. There are a few instrumental backgrounds. Sometimes you mismeasure the charge of a lepton, in particular if it's an electron, but one gets rid of many orders of magnitude of backgrounds. Okay, then we already discussed high lepton multiplicity, something that's also does not often occur in hadron-hadron collisions within the standard model. And also, although here we have an event with many jets. There's a top quark that has 1, 2, 3, 4, 5, 6 jets. Now, this is a signal event of a TTH process. That's in itself an extremely rare process. Such events are extremely uncommon. Once you see something, you can be sure that it is. Interesting. The 10 to the 10 events from the QCD. These are mostly tight-jet events. So signature with a high multiplicity, a high number of jets and leptons are also very rare. And then in the standard model, most of the decays happen promptly after the interaction. It rarely happens that a particle is created with a finite lifetime that can travel an observable distance in the detector and then make a displaced decay vertex. This is another feature that that can easily point to physics beyond the standard model in a background independent way, because it removes lots of backgrounds. Now, a general rule of life is if you have many of these requirements, then the backgrounds that are remaining, they are more and more complicated, because more and more things can go wrong in the detector and give you at a much lower rate, but you have to estimate it, rare background events that combine, I don't know, a rare decay with a rare mismeasurement. And then you have to estimate this, because if you claim a signal beyond the standard model, you want to make sure that you're not confusing it with a mismeasurement. Okay, so that's the end of our discussion of collisions. We are done with the highly energetic processes that happen in the standard model. We now move to something much more low energetic. We follow now our particle collisions from the collision vertex to the detector cells.